Okay, a summary on electric fields for today. So as we started out, we have electric fields and gravitational fields. We're relating this to gravitational fields because we understand gravitational fields quite well. Now, electrical fields and gravitational fields have similar properties. So we took both of those in turn and listed the similarities that they have. So electric fields are caused by charges. Anytime you have a charge, you have an electric field around that charge. Gravitational fields are caused by mass. The bigger a planet is, the more of a gravitational field it has. The size of the electric field depends upon the size of the charges that you have. The more charges you have, the more of an electric field you have. The more of a mass you have, the more of a gravitational field you have. They can both be presented by lines of force. Those lines of force for gravity are always going to be acting downwards towards the surface of the Earth. Lines of force for an electric field will act from positive through to negative. Lines of force are really just there to kind of show what the electric field looks like or what the gravitational field looks like, because that's something that we can't see. It's an abstract concept, but these just help us to figure out what direction that electric field is going in or what direction that gravitational field is going in. So electrical field strength is in newtons per coulomb, so there's a certain amount of force per coulomb of charge. For gravitational field strength, there's a certain amount of force per kilogram of mass. The direction of an electric field is acting from positive to negative, because if we look back at our electric field lines for positive and negative charges pull in and positive charges push out, just like the Van de Graaff did yesterday. Gravity always acts downwards, only ever acts in one direction. So we've got attraction and repulsion for electric fields. So we've got positive and negative charges. Remember, like charges push each other apart, unlike charges pull each other together. But gravity is different because it's always attractive. But the same rules can be applied to gravitational field strength as can be applied to electric field, as we looked at. So if we consider a uniform electric field, where a uniform electric field is a field that acts the same in all directions, if you put a charge into that field at any point, it's going to experience the same level of force, so there's no changes at all. We considered a uniform electric field from point A to point B, where point A is, say, a positively charged plate. We related it to the battery later. A negatively charged plate there. If we put a charge in here, if we put a positive charge in, or if we put a positive charge in there, it could be an electron also. So if we place a positive charge in that electric field, an electron is transferred from A to B or from B to A. If any charges move through there, then there must be some kind of work done, because there's going to be forces of attraction and repulsion here. Then we looked at both of the cases. So the first one there, if the charge goes from A through to B, then it gains kinetic energy because of the direction of the electric field. So we've got a positive charge here, and we've got negative charges here, so it's going to be attracted. We've also got two positive charges either side here, so that's going to be pushed away from there. So it's going to gain some sort of kinetic energy. There's going to be a force pushing it away. It's going to move, so it's got kinetic energy in the direction of the electric field. The second scenario that we looked at is moving that same charge, that positive charge, from B back to A again. If we move it from B to A, then energy has to be supplied to overcome the repulsion, the forces of repulsion. So it's attracted towards this negative charge at B here, but as it moves away from there, that force is going to decrease, but we're going to get a repulsion from this side here. So it's going to be all sorts of repulsion there, so you've got to put some kind of work done, some kind of energy put into that to make it move, to overcome those forces of repulsion. So we say that the charge gains potential energy, just as an object in a gravitational field would gain potential energy if you raised it to a height. So it's gaining potential energy, it's got the potential to move. If you let it go, it's going to be converted back into that kinetic energy to bring it across to the other side. Next of all, we decided that it requires 1 joule of work. If we strip it down to the simplest level, we need 1 joule of work to move one charge, a charge of 1 coulomb between 2 points. Say that's those 2 points A and B. We say that the potential difference is 1 volt. So if you put energy in to move a charge, then you are creating voltage. That's what voltage is. It's energy being supplied to those charges. So we say that 1 volt is equal to 1 joule per coulomb. That's a mathematical representation of this wee paragraph here. If we put that in symbol form, 1 volt is equal to 1 joule per coulomb. So there's 1 joule of energy per coulomb of charge. And that led us to the formula V equals W over Q, where W is the electrical potential energy, Q is the charge, and V is the potential difference, formerly known as voltage. So a rearrangement of that is W equals QV. So the electrical energy required to make that voltage is charge times voltage. We did a quick example on that, where we had 10 coulomb of charge moving from B to A. Just going back to the example that I started with, 60 joules of electrical potential energy is supplied to do this. Calculate the potential difference. So it's V equals W over Q. 60 divided by 10, which is basically 60 joules divided by 10 coulombs. 6 joules per coulomb, which is voltage. So in simple terms, voltage is the energy that is supplied to charges. So you've got 6 joules of energy being supplied to each coulomb of charge there. That creates 6 volts. So that's what voltage is. It's the energy that is put in to move charges from one side of, say, a battery through to another.